because of the existence of this process of spontaneous emission, a system such as an electron in an excited state can, in general, decay to lower states by spontaneous emission. This leads to the idea of a spontaneous emission lifetime. This is essentially the average time it takes a system to decay by spontaneous emission. To calculate the total rate of decay from higher to lower electron states, we must add up the spontaneous emission rates into all possible modes. To do that, we need to have a look at just what those modes are and how the matrix element varies for different modes.
We presume that we start off with the electron in an excited state, state 2, and no photons in any modes. The total spontaneous transition rate will be the sum of the transition rates into all possible final states Q through spontaneous emission. So we'll be summing over all the possible final states, and we'll have to look at the transition rates into those. And in our case here, the different possible final states will correspond to spontaneous emission into different specific modes lambda. Now, the specific transition rate into mode lambda is, as we figured out before, given by an expression like this. Since here we're presuming that the electron starts in state 2 and ends in state 1, this sum here over possible final states is just going to reduce to a sum over all possible photon modes lambda. So here's the expression we're going to try to evaluate, summing over all the possible photon modes. These numbers here, these matrix elements, may be different numbers for different modes, and we will have to only look at ones that have the right energy, of course. To calculate the transition rate, we start with the matrix element H ED lambda 1, 2. We presume the field, the electromagnetic field, is approximately uniform over the size scale of the quantum system. That's often a good approximation for an atom, for example. The wavelength of light is long, and an atom is small. So if the quantum system is centered at some position r0, that's the position of the atom if you like, we can just use the electromagnetic field at that point. And that simplifies the calculation of the matrix element. So in this matrix element here, where this is the electromagnetic field mode form, we can simply replace this inside the integral by a constant, which is the electromagnetic field mode form at the position of the atom, roughly speaking. And so we can move that outside the integral, and we're just left with this here, which is the integral with the wave functions of the initial and final states, and the position operator r in the middle.
For our calculation here, we'll presume that the modes of the electromagnetic field are all plane waves in unbounded free space. This is a standard assumption in most calculations of spontaneous emission, though there are situations where we would not do this. For example, if the electron system is inside some resonant cavity, the modes of interest will be those of the resonator, not of free space. Then the specific result we derive here does not necessarily apply. In that case, if the optical transition of interest lines up with a cavity resonance, then the interaction will be stronger, and we'll get faster spontaneous emission, an effect known as Purcell enhancement. It's also possible to inhibit spontaneous emission by making sure that the photon energies of the modes of the resonator do not coincide with the optical transition energy, or by ensuring that the emitting system lies near some field minimum in the resonant modes. The quantum mechanical formalism we've set up here can handle these enhanced or inhibited emissions. We would just have to use the resonator modes for our electromagnetic field rather than plane waves. Here, though, we'll just presume plane wave modes in ordinary free space. This approach directly covers most of the spontaneous emission we come across.
We need a normalizable form for plane wave modes. we imagine we have a cubic box of volume VB, and it's common for mathematical convenience to use running waves with periodic boundary conditions, though one could use standing waves and get the same result for a large box. The resulting modes have the form like this. Here's our u lambda of r, and we have a unit vector out here, this Gothic E, which is a unit vector in the polarization direction of the electric field, whatever that is, and we have a propagation vector for the electromagnetic field, k lambda. And of course, for waves in free space, this vector here is going to be at right angles to the propagation direction. Now, these modes are normalized over the box of volume VB. The allowed values of kx, for example, the wave vector in the x direction, are spaced by 2 pi over Lx, the length in the x direction, and similarly for the y and z directions. And that leads to a density of modes in k space of the volume of the box divided by 2 pi all cubed. For such propagating waves, we will also have two distinct polarization directions, though we will handle polarization properties directly. We're going to approximate the sum over the modes lambda by an integral over k with this density of states. So we're presuming a large box, essentially. And we will also formally sum over the two possible polarization directions. That is, this sum over possible modes will correspond to a sum over the two polarization directions we choose as our basis here, and we'll be approximating the rest of the sum by an integral, which is okay provided that the box is large. In considering the polarizations, we will choose polarization directions at right angles to one another, which is typical for looking at electromagnetic waves, and at right angles to the propagation direction. In fact, plane waves in free space for electromagnetism have to obey these conditions if they're propagating waves. The polarization direction has to be perpendicular to the propagation direction, and there are two orthogonal polarization directions we can then choose. Specifically, we're going to choose polarization directions relative to the vector matrix elements R1, 2 here. We're going to choose one polarization, which is a vector here written with a Gothic bold P, to be in the plane of these two vectors, the propagation direction and the matrix element direction. So here we imagine we've drawn the propagation wave vector here, k lambda, and we've also drawn the vector that is R1, 2. And we're going to choose one of our polarization directions to be in this plane. It has to be perpendicular to the propagation direction, and we'll choose it to be in this plane. With this choice, the other polarization, which also has to be perpendicular to the propagation direction and perpendicular to this vector, is then sticking out of the plane or sticking into the plane. And so, in that case, this product, this vector dot product, vanishes entirely for this other polarization. So that is, for the other polarization we could have for the light field, there's absolutely no interaction of that polarization with this R1, 2 matrix element. Hence, in our summation, we need now only retain the first polarization direction we thought of, this one. For this choice, we therefore find that this dot product of the electromagnetic mode form with the matrix element, vector matrix element, R1, 2, just reduces to this form, where these non-bold quantities here are just the magnitudes of these vectors, and we have a sine theta, which is the angle between the propagation direction and this vector R1, 2 we got out of our matrix element. Now we can use all these results to rewrite the total spontaneous transition rate. That is, this expression here, summing over our modes, becomes this integral here. So we still get our 2 pi over h bar out the front. We are integrating using the density of states. And we have our delta function, and we have our matrix element. And we have our propagating wave in here. That is the amplitude of the electromagnetic wave at position R0. And this reduces to this integral here. The modulus squared of this e to the I k lambda dot R0, of course, is just 1. That simplifies things. We have this square root of VB squared, cancels out with that one. And we have various other terms in here. The term that is left, that is important, is this sine squared theta. And of course, we still have the delta function in here to deal with. And we can formally then write out this integral over all the possible k values as an integral of the magnitude of k lambda from 0 up to infinity, and then an integral in the theta direction from theta equals 0 to pi here. And we've already performed the integral in the other angular direction, the phi direction if you like. That gives us the 2 pi here. In this integral, we can now formally change variables. We know that for propagating waves, the frequency associated with them, for free space waves, is the velocity of light times the magnitude of the wave vector. So we can formally change variables in this integral from the k lambda variable here to an h bar omega lambda variable, if we like, which of course is just an energy variable. And that gives us the integral in the following form. Note that we've now separated out the sine cubed of theta, these two terms here multiplied together, so we've got this integral to figure out. Nothing else in here depends upon theta. And our k lambda squared here essentially turned into this, and our omega lambda turned into this, and we've got some h bars to the fourth down the bottom to cancel out these h bars on the top. Given that we can perform this integral and the answer is 4/3, we finally have the total spontaneous emission rate. And here's all that we are left with. This whole integral here over h bar omega lambda with the delta function in it, of course, is very simple. H bar omega lambda equals this energy separation here. And so we finally have this result. And here, omega 1, 2 is the E2 minus E1 over h bar that we got out of this delta function in the integrand. Such a rate gives a natural lifetime, sometimes called tau or tau natural here, for a state. And that is just 1 over the transition rate, the total transition rate. So a quantum mechanical system sitting in empty space in an excited state will decay on average over this time scale to its lower state, emitting a photon. The direction of the mode into which the photon is emitted is random, although it is weighted somewhat by the polarization effects that we have taken account of in our derivation here.